Ready.
Okay. Am I audible? Am I audible?
Yes.
Hello? Am I audible?
Yes.
Okay, thank you.
ইউটিউবে কেউ একজন গিয়ে বলো।
Good
Streaming
morning to
started.
all of you. May I start? May I start?
Yes, sir. Definitely. You may start.
Yes, sir.
Okay, okay. Thank you. Thank you. Good morning to all of you. On behalf of the Department of Mathematics, City College, and IQAC City College, I, Mushtiroman Sardar, Joint Convener of Organizing Secretaries
চলছে,
and
তুমি বলে দাও,
Assistant
চলছে বলে দাও।
of this college, welcome all of you in this national webinar. Our young distinguished speaker, Dr. Tanmoy Sarkar from IIT Jammu, is present with us. We express our sincere thanks to him. All of you know that we are facing a very difficult situation due to COVID-19. We cannot go to our workplace. We are doing all from our home. This webinar is also such one. As many students are present here, so I want to remember few general precautions about COVID-19, which we are following in this pandemic situation. Wash your hands with soap regularly, practice social distancing, wear masks in public, don't go out unless absolutely necessary. Now we start this webinar with welcome address by our principal, Dr. Shital Chattopadhyay. As he is busy today due to college work, so he has sent a welcome address for our webinar in the form of voice message. I request Mr. Sandeep Prasad, HOD, Department of Hindi, and Joint Convener of Technical Committee, to play the voice message. Mr. Prasad, do the needful. Sir, voice is not audible. Mr. Sandeep Prasad. Mr. Prasad, sir, voice is not audible.
Okay. Okay. Now it is audio message of our principal.
Very good afternoon and warm welcome to everyone in this one-day online webinar on Foundation of Ordinary Differential Equation (ODE) with a case study. It is my privilege to patronize this socially and holistically enriched forenoon on behalf of City College, Kolkata. My heartiest welcome to all my fellow colleagues, my beloved students, organizers, and all the participants of this one-day online seminar in the present critical situation due to COVID-19 outbreak. Our college has already completed 6 online seminars, mostly in relation to COVID-19 pandemic, a couple of days ago, and today's seminar, organized by the Mathematics Department of City College, is in the field of mathematics on differential equations that relates one or more functions that would be helpful to the honors and general students of mathematics and related fields. I must heartily welcome the Honorable Speaker, Dr. Tanmoy Sarkar, Assistant Professor, Department of Mathematics, Indian Institute of Technology, Jammu, for his kind acceptance to deliver the lecture in the field of mathematics and related to the present COVID pandemic situation according to his choice. I wish Dr. Sarkar will make all emotive through his valuable talk on ordinary differential equations. Finally, I must mention the effort of organizers from Department of Mathematics along with the IQAC and the seminar committee to convert this forenoon a great accomplishment. I am sure all will enjoy the lecture and will be benefited. Welcome you all again for cordial participation. I wish a great success of the seminar. Thank you.
Okay, we
I
express
want
our
I want to apologize. The spelling of India was wrong there. It is just a typological error. So sorry for this. Now it is to you, Monsieur sir.
okay, thank you. We express our sincere thanks to our principal sir for his valuable welcome speech. Now I request Dr. Tapan Kumar Ghosh, joint convener of this webinar, coordinator of IQAC and HOD Department of Physiology, to speak few words about our today's webinar. Sir, over to you.
Okay, thank you. Good morning, everybody. Thank you, Principal Sir, for your enlightening welcome address. I, on behalf of IQAC City College, am pleased to heartily welcome today's speaker, Dr. Tanmoy Sarkar of the Department of Mathematics, IIT Jammu, and all the audience who I hope will spend quality time this morning. I also appreciate the work done by the Department of Mathematics City College for organizing such an important webinar. Dr. Sarkar will be speaking about foundation of ODE with a case study. ODE, or ordinary differential equation, is a differential equation containing one or more functions of one independent variable and the derivatives of those functions. The term ordinary is used in contrast with the term partial differential equation, which may be with respect to more than one independent variable. Now, ODE is not restricted to mathematicians only. Scientific fields of ODE include much in physics, astronomy, meteorology, chemistry, ecology, population modeling, economics, biology, including infectious diseases, genetic variations, etc., etc. So ODE is widely spread over the scientific and intellectual world. I am confident that the talk of our speaker, Dr. Sarkar, will enlighten all spheres of scientific arena. With these few words, I once again welcome Dr. Sarkar and the audience with a hope that this webinar ends with a great success. Thank you very much.
Thank you,
Over
sir.
to you, Mustif.
Okay. Thank you, sir, for your valuable speech. With your cooperation, we could not arrange this webinar. Thank you so much, sir. Now I request Mr. Shamsundar Dhara, the organizing secretary and assistant professor of mathematics of this college, to give an introduction about our respected speaker.
Thank you, sir. Good morning to all of you present over here in this webinar. Thank you very much for giving me the opportunity to introduce Dr. Sarkar. He happened to be my classmate during my MSc study at IIT Madras. He is one of my bosom friends, and this is a moment of pride for me to speak of him. I am very proud of having such a good friend. I am also thankful to Dr. Sarkar for accepting my proposal of coming over in this national level intellectual exercise as a resource person being organized by the Department of Mathematics of City College in collaboration with IQAC of the college. Dr. Sarkar obtained his MSc degree and PhD degree in mathematics from IIT Madras. He held the esteemed position of project associate at IIT Madras. Subsequently, he held postdoctoral positions at TIFR, Center for Applicable Mathematics, and Indian Institute of Science, Bangalore. In 2018, he joined IIT Jammu as an assistant professor in mathematics. His research interested areas are partial differential equations and numerical analysis. He has many national and international publications to his credit in various recognized journals. Thank you all of you once again, and hope all of you enjoy the presentation. Thank you.
Thanks, Mr. Dhara, for your nice introduction about our today's speaker. Now I request our honorable speaker to deliver his lecture on foundation of ODE with a case study. Sir, please start.
Thank you, Mushur Babu, for inviting me, and all the organizers for inviting me for this lecture. And it is my pleasure to share some of my experience with the differential equation with the students, in particular. The students, this talk is mainly intended for the students, and the others, if however they are mostly familiar with the faculties and teachers. So I also thank the principal, sir, Dr. Prasad, for nice appreciation of this webinar. And also I will appreciate Topun Babu for basically giving some brief idea about ODEs. Okay, and that is very nice introduction, I can say, for ODEs, that it has definitely it has application across the disciplines, and we will mostly talk about this. Okay, so I am starting the lectures now. So Shandipji, you can enable the sharing the screen. So the screen is visible to all of you?
Yes, your screen is visible.
Okay. So thank you. So I welcome you all for this lecture in mathematics. So the title of my talk, as you can see, it is basically Foundation of Ordinary Differential Equations with a Case Study. So, and I particularly thank Department of Mathematics, City College, and IQAC for City College for nicely organizing this and for this kind invitation. So in this talk, I will talk about ordinary differential equations. So first, we want to know what is ordinary differential equations. And in this talk, I will also give some glimpses of how it has been originated or it has been founded. Okay? And at the later stage of the talk, I will give one case study, okay, which you can relate with current situation to some extent. Okay? So what is first, we want to know what is
Dr. Sarkar, your voice is not coming. You are not audible now.
of a circle changes with the size of the radius. So in language of mathematics, changing entities are called variables. Okay, and this rate of change of one variable with respect to another variable is basically called a derivative. Okay, which so the equations which express a relationship among these variables and their derivatives are called differential equations. Okay, so that is the brief introduction of differential equation. Okay, so mostly we will take care of the ordinary differential equation. Of course, we will comment little bit about partial differential equation later on. So you can see that this many interesting problem and important real life problem can be modeled through ordinary differential equations. Okay, and ODE in particular has a deep connection with geometry and other areas. So it is across the discipline this ODE comes into the picture. It comes in physics, chemistry, engineering, in various departments, as various discipline, as mentioned by earlier by Tapun Babu and so on. Okay, so basically, what we want to see it here that we have a current situation. Okay?
Hello, Tanmay sir.
Yes.
Are you presenting your screen? Are you just?
Yeah, no, I have not yet started. Yeah.
Okay.
Yeah.
Okay, sorry, sir.
So yeah. So thank you. Yeah. So basically, what we want to see that, given a current phenomenon, we want to see in future how the things will, how we can predict its future and so on. Okay, so how this phenomena will be changing in the future. Okay, so this type of things, or the dynamical behavior of certain quantities or certain variables. So that's what we want to basically study here. So in ODEs, as you know that it has got developed over the years from beginning of from say 17th century and so on. So yet there are several situation arises where we still cannot have answers. So the answer of few questions are still awaited. Okay, and so with this I'm starting basically this is the outline of my talk. So I will first introduce about little about ODEs, then I will talk about origin and historical remarks of ODEs. Okay, and then we'll discuss some fundamental issues or some issues as we have encountered during the ODEs when we have learned ODE and so on. Okay, then I will discuss with a case study, and after that we will discuss about qualitative analysis. So what is qualitative analysis? So as you know that even after getting the solution, we need to look for certain things. Okay, it is not in there when we get some solution. We want to still understand its behavior of the solution and so on, how it behaves and how the time approaches, how its behavior changes. That is basically the dynamical behavior of it. Okay, and then I will have some concluding remarks of it. Okay, so now so what is ODE? So most of you have already familiar with ordinary differential equations, okay, as you have studied in some extent in from school to colleges, okay. So and mostly it is basically we feel that is it a collection of few methods in ODE, because we always try to, when ODE comes in our mind, we always try to solve them or find a method to solve them. So that is the question first, that is it only a collection of few methods in ODE or is it something else is also there? Okay, and it is unfortunate in most of the many places across the our country that this subject has been taught only through the methods. So that is not the case. So that is the only intention of basically giving such talk here, that to motivate you that it is not only a collection of methods, here is lot of mathematics behind it. Okay, so this ODE is a very basic or fundamental branch of mathematics. So, and to understand ODE, it is not only it is a method, we also need some prerequisite to understand it. And that is basically, as you have all come across some linear algebra and linear real analysis, which you have always have studied in the colleges. But even if you have not familiar with this, that is should not only to you to understand this lecture. So basically in ODEs there is lot of connection between real analysis and linear algebra. So that connections will be evident when we will go through it. Okay. Okay. So why we are studying ODEs? Okay. So when ODE has actually originated, that time the definition of functions and other things, what we know now, it is not there at that time. Okay, so the whatever analysis or functional analysis later on, you will see that this complete subjects got developed from when it differentials equation originated. It has been this complete analysis branch has created from that. Then as we have already mentioned that it models the physical system. Okay, many physical system can be modeled by differential equation. And of course, whenever your problems will be changing, so your differential equation system will be different, and each system has their own challenges and own applicability. So that is the thing. So for instance, you need laws of natural and physical world in the form of differential equation you can see. And very famous example we can see basically Newton's second law of motion, okay, which we will focus little bit on it in the later. Okay, so first let us start with some historical remarks. Okay, so this is basically the ODE has started during the era of Newton and Leibniz. So basically they are the inventors of differential and integral calculus. So so Newton is basically, you can see the picture here, that this work has been started in the 17th century, around 1670s. Okay, so this ODEs has come into the picture. So it is basically from the reliable sources, it is we can know that this Leibniz is basically the originator of the differential equation. Okay, so we'll see slowly that how they have contributed to develop this ordinary differential equation. Okay, so what we have seen, it has been first started with Newton and Leibniz, but later there is Bernoulli's brothers and their family members. They have actually contributed a lot to basically advancement of the ODEs. Okay, so there is in the ODE history, there is basically two phases is there in ODEs. Okay, so I will talk about the first phase of ODEs. So Newton, in the 17th century, he has classified few ODEs. Okay, so first ODEs, you can see that it is basically y is a function of x. Okay, and y is basically dependent variable and x is independent variable. So dy dx equal to fx. Then he also have gone through this dy dx equal to fxy and x dou u to x and y dou u to y equal to u. So basically first two in the differential equation, what you can see, it is basically y is only function of x. So these are called ODEs. And the third one here, u is basically function of x and y. So it is comes under PDE. Okay, partial differential equations. Okay, so we'll not talk about much into partial differential equations because that is a much more celebrated topics, and maybe we will have some other time to discuss. So first, when Newton has come across such kind of ODEs, his idea to proceed for solution is via elementary functions. What are those elementary functions? So elementary functions are basically this sum, product, or composition of several trigonometric functions or polynomial functions, rational functions. So his idea is basically to approach the solution via some elementary functions, maybe polynomial or the trigonometric functions. So this differential equation is assumed that he has this work around 1670, but it got published in very later stage, around 1736. This is a very famous reference of this earlier in the ODE's origin, that the method of Fluxions and infinite series. So infinite series, you can see that you can always get this infinite series thing because he was thinking of going for the solution through elementary functions. Okay, so in 1676, this Leibniz introduced the term differential equations. Okay, so here it was not there, even though this work of Newton was discussing about this equation, but it is basically Fluxian equations name he has carried on. But this differential equations name basically introduced by Leibniz in 1670. And so in 1693, this Leibniz, which basically a German mathematician who solved first differential equation, and that same year Newton also published various results of differential equations and solution method. His solution method is mostly via elementary functions. So from 1693, this differential equation got recognized as a distinct field in mathematics. Okay. So not only Newton has stopped there, he has carried on with this differential equation, and he observed some of the fundamental things there, that differential equation has a infinite number of solutions can have. Okay. So as you know already, if you are familiar with it, that the arbitrary constant will come, and so you can generate infinite number of solutions. Okay. So he has observed such things even for non-homogeneous things, but this general solution of a certain differential equation, that took time to come to realize that what is basically a general solution. As you right now, as you are familiar in ODEs, that general solution basically consists of your homogeneous part, then non-homogeneous part. So it has complementary functions and particular solutions and so on. So this general solution has slowly developed, but in the initial stage, Newton has observed that it can have infinite number of solutions. Okay? And in some cases, he has able to do it, which we know as a series solution in recent time in ODE, is that what we are doing in series solution, that we basically try to understand or try to represent the unknown solution, okay, in terms of say various trigonometric functions or polynomial functions. Then we try to basically determine the coefficient. So that way it basically series solution comes. So that is the basically beginning of the differential equation, how they have approached it. Okay, so after that era, so then Bernoulli brothers, basically James Bernoulli and John Bernoulli, they have taken up this differential. So in between this, the first person, this James Bernoulli, who actually contacted Leibniz to get an idea of this subject of differential equation. But during that time, Leibniz was traveling. Actually, Leibniz was a German mathematician, and these Bernoulli's brothers are basically from Swiss family. Okay, so he wrote a letter to Leibniz, but Leibniz was traveling, so from 2-3 years his letter was not answered. Okay, so in between, John Bernoulli has taken up these subjects and he has made some significant contribution during that stage. Okay, so what is his contribution? That he started that method of integrating homogeneous differential equation of first order. So what we do now in first order, that if this homogeneous form, if it is in exact form, how we go for solution. So such kind of things, how to go for, because remember the integration concept was not very well developed that time. Okay, this in the 17th century. Okay, and also what he has done, that these elementary methods, several elementary methods has been developed by these Bernoulli's several family members during that time. And then separation of variables. So it is basically this separation of variables was observed by Leibniz, and then later on with the iterations, as you see that once the idea comes, it comes and then it got generalized and so on. Then it comes to a final form. So this separation of variables is also like that. It very earlier it was observed by Leibniz, then there is Bernoulli brothers and so on. They make it in a final form, which we study now also. This. Then in 1695, these Bernoulli's equations we have all come across in or differential equation topics, that what is Bernoulli's equation. So it is basically a dy dx plus px into y. This px is a function of x, and right side f of x is also a function of x, and y power n is some, you can say n is some. So this equation is introduced by Bernoulli's brothers, okay, and it came from celestial mechanics. This equation, and this equation actually was solved by Leibniz in the next year itself. Okay? And we study this equation also in this time. Okay, okay. So now I will make some initial developments. What has been done during that period of Leibniz and Bernoulli's. Okay, so we have seen some whatever their contribution, and that has been carried out in the 18th century. So in the beginning of 18th century, the first book of differential equation has come, that is by Gabriele Manfredi. Okay, and that is basically, this book is basically of what is the contribution of Leibniz, Bernoulli's. That contribution is basically there in this. So in the 18th century, this differential equation what has mostly been carried out or been basically by Leonardo Euler, D. Bernoulli, and then J. Lagrange and P. Laplace and many others. Okay. So what in 1739, the Euler began using this integrating factor. So what we know as integrating factor of a differential equation, so that has been basically introduced by Leonardo Euler. Okay, okay. And then we also come across in differential equation this exact differential things. So this has come from basically where they have studied basically exact differential model of heat and so on. Okay, and we know that if some differential equation is in exact form, or so then we have or total differential equation, we say, then it is easy to find out that how the solution will look like and so on. Okay. Euler has further contribution in differential equation, that what he has done, that reducing a particular class of second order ODE to a first order ODE. So we still do such kind of method, that if we some way, if we can find out a one solution of a second order ODE, then we try to find out another solution based on the first solution. Okay. So that method is basically again this is introduced by Euler. Okay. And then we have all come across Euler-Lagrange representation of general solution of non-homogeneous ODE. Okay, so this also has been done, and then also we have seen this important method in ODE, variation of parameters, how you vary the parameters and get the solution basically. So this variation of parameters also come across several iterations, but this finally it came in the beginning of the 19th century, and that is being given by Lagrange. So mostly these methods we all come across in even in the recent time. In any ODE course we will come across such methods. So this is basically, you can see that this early in the latter stage of 17th century and throughout 18th century, the contribution of differential equation in this subject has got advanced and so on. Several important methods got developed and so on. Okay. Okay, so then comes the development in the second phase. So in the second phase, what happens that in this Euler, Lagrange, and Laplace, and many others, they soon realized that there is no hope in to solve all the differential equation they are coming up with. Okay, so it is never there is no explicit way to solve these differential equations. So they realized in the beginning of the 19th century itself, okay, that many differential equations may come and there is no hope to discover the solution techniques for such differential equation. So explicit solution is not possible. Even now, there are several differential equations are there that we do not have any explicit solutions, okay. Okay, so that means limitations of solution in explicit form. We cannot solve a differential equation in explicit way. Means we cannot give a solution y equal to with some function of x and so on. So what happens then? So that should not stop you, because even if you don't know exactly what the solution will look like or solution form is not known, but that should not stop us to analyze its existence of solution and whether if the solution exists of some differential equation, whether it is unique. Okay? So those ideas we can question, and that has a lot of impact. Like for instance, stability properties, and then asymptotic behavior, and how the solution goes on as time progresses, okay, and stability of the properties. So this kind of qualitative analysis is very important for ODEs. Okay. And in the beginning of 19th century, by that time, when ODE has originated, that time this calculus has not been developed as we see today. So by the beginning of the 19th century, this calculus has been got developed, and this differential equation has been studied through mathematical analysis. So this real analysis, as we discussed in earlier, that comes into a picture of differential equation. Okay, and that got so much impact on differential equation. It all together it started in a different way. Okay. So first, in the second phase, the most important contribution in the 19th century is that the first existence theorem of first order ODE came due to Cauchy in 1820. So if we go in the much advancement of ODEs, okay, then we see that solution of a certain differential equation may not always exist. So it can exist in a certain circumstances. So such things as first that under which condition solution exists and so on, it has been given by Cauchy in 1820. And later, this existence and uniqueness theorem has basically this got much more in a general form by Picard and Lindelof, okay, with this existence theorem. Okay, so then I will just make some remark here that the notation we know today that differential equation that UI gets, it is actually introduced by Leibniz in 1675. Okay, then how this differential equation came when we have this differential calculus, integration calculus has slowly got slowly developing. Then somebody, it is anybody's question that suppose I have a function f. So does there exist any function g such that g prime t equal to f of t? G prime means this is derivative of g. Okay. So it is basically a calculus problem, if you see, or integral calculus problem, that if I have a function, whether it has some antiderivative. Okay. So from that itself, this differential integral calculus problem comes, and from this it's actually the starting of a differential equation. That suppose I have a function f of t, can I find g of t? So g of t is basically unknown function. So as we said, this Newton's second law, you see that this is well known or celebrated Newton's second law of motions. It is basically ddt of mt. This v is the velocity, u is the mass, and f is basically the force. Okay. X is the displacement. So x double dot it is basically with respect to time derivative, and we have, if this force is only function of time, so then again this is a integral calculus problem, right? Because you have to integrate it again and again to get your basically x. And this type of, when we have this higher order differential equations, one can do such kind of study of differential equation. They can make higher order differential equation into a system of first order differential equation. That is not difficult to see. You have it is just, you have to introduce some specific variable to make any higher order differential equation of ODEs to make a system of first order differential equation. What happens if we make a system of first order differential equation, then we have a certain dynamical behavior we can study. Okay. Okay. So a large number of, not only this Newton's second law and so on, a large number of physical, biological phenomena which can be modeled via differential equation. For instance, this radiation decay, tumor growth, mechanical vibration, motion of artificial satellites. So this ODE has been used. Even one very important center, ISRO, so they use this idea of ODE to project these artificial satellites and so on. This ODE comes into a much more in a impactful way with the controls and other things. Okay. Okay. So now I want to define what is ODE after this historical thing. So now let us let go into little mathematical way, that, or in language of mathematics, that what is ODE? ODE is basically, you have a variable y, which we call is dependent variable, which is a function of t. T is an independent variable, and suppose we have a function, okay, function f, which is of ty dy dt, d2y dt2, and up to say dny dtn. Okay. So if this is a function, so this will be called as ODE, ordinary differential equation, and this n is a natural number. It is called the order of differential. So first let us try to consider this first order ordinary differential equation. So as we see from the above, so it can have a form of function of ty and dy dt is 0. So many of the times we write the differential equation in terms of dy dt equal to g of ty. Remember, these two form is not same. Okay. These two form is not same. So many times you cannot have this second form cannot be obtained from the first form. So that actually, if you find the second form from the first thing, that is through implicit function theorem, and so on. If you see that, not always a variable can be expressed in other variables there in a function. Okay, and also another important things you will see in a differential equation, that whether that differential equation is linear or non-linear. That has lot of impact, because in the courses what we have studied usually the linear differential equation. So this, when we study linearity, and then this linear algebra comes out, okay, that what operates in a solution that has been having linear properties, okay. Okay, now let us go into the thing. Suppose we have a very simple ordinary differential equation. Let's say dy dt equal to small f of t. Okay, so we can integrate it easily if we know the integration, and if f is integrable, then only we have a solution. We can integrate it. Suppose we are integrating it, what we write, yt equal to integration f of t dt plus c. Is basically an arbitrary constant. So this arbitrary constant can vary in a different way. So for instance, if you attach initial value with this differential equation, so the starting point of the differential equation will vary, because you will be able to determine your arbitrary constant. Okay, so that is what this initial value problem means, that it has involved with this initial value things. Okay, yt naught. So you can see the trajectory in the figure, that if you vary your initial data, then your solution y of t will also vary accordingly. Okay, so now as we see that in a first order differential equation, you have seen that one arbitrary constant comes, and you may be thinking that maybe all the ordinary differential equation have arbitrary or infinite number of solutions. It is arbitrary. So the thing is that for in a certain example, we can see that this is not the case actually. So if you take such example of mod y dash plus 1 equal to 0, so then what can you say about its solution? It has no solution. So you can easily verify it, that such kind of differential equation also there. It is a first order differential equation, but still it has no solution. Okay. Okay. Let us go for the another. So what we have seen, that in a first order differential equation, one arbitrary constant is coming. As we have also seen in differential equation courses, that if we go for higher order, then the order of the differential equation, that many number of arbitrary constant may come into the picture, right? That's what you may think that. But let us take this example of y double dash square plus y square equal to 0. Okay, so you can see that though it is a second order differential equation, it has only one solution, and that is y equal to 0. Okay, you can see that. So it does not mean that whenever you have a differential equation, it will have arbitrary solutions. So it may not have solution, it may have a unique solution, you never know. Okay, so let us take another example. Suppose you have x y dash equal to 1. Okay, so what you will get, you will basically, you will see that it has no solution when you choose your interval -1 less than x less than 1. Basically around 0 you will have no solution. If you choose, you can easily see that it is nothing but y dash equal to 1 by x. So if you integrate, you will get basically log x plus. So this log x will be not defined at x equal to 0, right? So but it is very nicely defined when you go for the positive x and so on. So that means a solution may not be defined for whole real line, but it can define in a certain interval. Okay, so this type of things can happen in the solution structure. Okay, another example we can see that so this is basically again a first order differential equation. If you see that, so this first order differential equation can also have two arbitrary constant. Okay, it is not that always we have a one arbitrary constant in a solution of a first order differential equation. So we can have more than one arbitrary constant may appear in the solution. So in this all these examples, what you can actually observe, this type of things, it's not much encountered in the ODE course, because all the example of this differential equation, okay, is basically some extent involve non-linearity or some problem in the function itself, okay, whether it is not continuous some point and so on, okay. Mostly it is non-linear. So when we go from linearity to non-linearity, the behavior is completely unpredictable. You cannot predict the behavior of it, okay. So what we can see basically in a solution concept. So first, already we have seen that when you express or able to solve y in terms of x, we call it as an explicit solution, okay. And there is also implicit solution. We cannot solve y in terms of x, but as a function of xy, we can get a solution. So that is basically called a implicit solution of a differential equation. And even if you don't able to get any explicit or implicit solution, then usually one go to numerical solution. So these are the solution concept of ordinary differential equation, okay. So as you have seen, this differential equation may come from a different problems from across the area it may come. So it is not that all the differential equations will have a solution, right? So that's why this existence is very important. So before we try to go for anything else, we try to analyze whether the solution exists for such differential equation. So that's why this existence theorem comes into the picture. And when the solution exists, then we try to analyze whether the solution is unique for this differential equation, because uniqueness is very important. Otherwise, what happens if you go for numerical solution or anything? So one numerical method give another solution, and another numerical method give another solution. Such kind of things may happen, okay. And then continuous dependence, okay. This is also very important, as we have discussed the stability property. So suppose you have a differential equation and there is some initial value or right hand side some functions are there. Suppose you change your functions little bit, or initial condition in a little bit, you are changing the initial condition. You want to know how your solution will be changing, okay. So you want your solutions to be stable. So if I change little initial condition, your solution, if it change in a huge way, that means the solution you have got is not very stable, right? And why is stability is very important? Because you want to apply such kind of differential equation in a real life problem. So when you try to apply in a real life problem, the initial value you will observe from a statistical data or experimental data. So it may not be exact data you will get. So if your solution is not stable, so then the solution, we cannot believe the solution. We cannot deal with such kind of solution. So that's why stability is very important. So similarly, this qualitative analysis or behavior of the solution is very important to us. That where we basically study this existence, uniqueness, and stability, and their asymptotic behavior and so on. Suppose if I go t tends to infinity, how the solution looks like and so on. Okay. Okay. Suppose you have a example one. Suppose I will make some few remarks which you come across in a ODE course. Let's suppose you have a differential equation dy dt equal to 1 upon y sine y square. Okay. So then what you will do? Usually what we do, that we write the second step, then we write the third step. Now the question is, we understand what is dy dt, right? And that meaning we can know. And the third step also we have a meaning that we know. But what about the meaning of the second step? That we don't know, right? That what does that mean? Y sine y square dy equal to dt. That we do not know. Because we'll see that, because small dy does not have any meaning, or small dt does not have any meaning. With the integration, it has meaning. So the rate expression does not have any meaning. Similarly, if we try to further proceed, what we will do? We will substitute y square equal to t, and then immediately we will write 2y dy equal to dt. So what does that 2y dy equal to dt means actually? So that we want to know, because usually that does not have any meaning. And as we see that there is this rate expression does not meaningful, okay? But we know what is the meaning of dy dt. That you all also have studied across the branches, that dy dt is nothing but, you can define through a limit, that it is nothing but y at in a small part of time t plus delta t and yt, and it is divided. So dy dt is a meaningful expression. So 3.1 is completely meaningful, and then 3.3 is also meaningful. But what about 3.2? We all write such kind of expression, but that does not have any meaning. So we want to understand why we write such thing then again and again. So that we'll try to address such questions. Okay. Okay. Another thing is that, suppose you have another example, dy dt equal to say a of y, okay, a into y. So what we do usually, that we write 1 by y dy a, okay, and then we integrate. Again, this rate expression does not have any meaning, because you cannot have any meaning of dy, right? And it is only having meaning with the integration, okay, and with the earlier form. So what we do for this example, we immediately differentiate or integrate this equation. We immediately write log of y of t equal to at plus some arbitrary constant c naught, and from there we get yt equal to c into exponential of e power 8. Okay, exponential of 80, where c is any arbitrary constant. So this is the right solution. There is nothing wrong in this solution, but we want to understand this is all of us will actually go for the solution in this manner, but we want to understand there is some certain things we need to address, or even for such simple examples. Okay, so what we do basically, we are integrating 1 upon y dy. So this only, if we do integration, it should be log of mod y of t. It is not, because log is only defined greater than 0 quantities, right? So it cannot be defined for y of t. We don't know about y for the time being right now, right? So if we do integration, it should be mod of y. So then what we are getting, mod of yt equal to c into exponential of t. Okay, so that's what we are getting our solution. But then we already got our solution yt equal to c exponential of at. Whether these two solution is same, so that is usual question, and that is actually same. Okay, we will see that. We'll address such thing, that first let us try to understand what this dy dt means. Okay. So when we write y squared equal to t, if we remember the substitution we are making y squared equal to t, so that means you are basically changing the variables, right? You are going from y to t. Okay, so suppose y is function of g of t. So then what is your f of y? F of y will be f of g of t. Okay. And it is nothing but, if we define it by ht, then it is h of t. So when we do change of variable, so we know the change of variable, yeah, that is integration of f of y dy. If we do change of variable, then it is basically f of gt into g prime of t dt. Okay. So this change of variable is not a very not a very simple formula. It can be easily derived. It requires a proof of this change of variable. Okay, so what we are writing as dy equal to a dt and so on, this is basically representation of change of variable. Okay, what we are doing, we just write dy equal to g prime t dt. Okay, so that is what is basically we write. We so it does not have any meaning. It is just a symbolic representation of the very change of variables. So usually instead of integration on f of y, we just write dy equal to g prime of t dt. So that's what the thing. So usually what does that mean? It means that the change of variable is happening with the integration sign. So usually dy, if you write dy equal to g prime t dt, it does not have any meaning. So in behind this thing is going on, this change of variable things is going on. And remember that this is a very standard formula and it is not easy to prove. Okay, it requires some proof. Okay, so it is basically symbolic representation that dy equal to g prime t. It does not have any other meaning. Okay. Okay. Another problem we have encountered, we have got our solution mod of yt equal to c exponential of at. That is the correct solution because we are doing the integration and we got log and so on. So then what we can do actually, we take exponential of at in the left hand side, then we get yt into exponential of minus at equal to constant. So now you can see that y is a differentiable function because it is a solution of the differential equation, and exponential of minus at, it is also a nice function, differentiable function. So then we are getting modulus of a certain function is constant, right? So then we use a result from a real analysis that if a real valued function f, which is continuous, and mod of f is constant, then eventually this f is a constant. So what we will get? We will get yt into exponential of minus at equal to constant. And then actually we get yt equal to c into exponential of at. So that way, this actual solution, what we write, that comes actually. So it does not come from just integration there, okay? But eventually you get into a correct solution. So this is the step in behind to understand how that solution has come into the picture. So I just took some few examples to make you understand that how this symbolic representation and how the solution usually comes. So now at the end of the talk, I just want to discuss one case study like a population growth model. Okay, even so you might have come across such kind of things that any population or any species, how it grows and so on, so that those kind of phenomena can be modeled through ordinary differential equations. So we can see even in the current situation or even in the current scenarios that many epidemic things and so on has been studied through ordinary differential equations. So here we just discuss little simpler thing that suppose yt is a population size of a given species at time t, and suppose rate of change of population is proportional to population size. Okay, so how this population is changing, it is basically proportional to the population size. So and r denotes the difference between birth rate and death rate of that population, how the species and populations are growing. So R is known to us. So usually what happens, as I told earlier, when you try to model certain physical phenomena or some real life problem, what you do, you try to take the data from experimental or some statistical data. So this R actually comes from the experimental data or statistical data. And suppose you have a initial time, you can see what is your population at a certain time, at time t naught. Suppose you are measuring the population, that is y naught. Okay, now you want to predict your future, that what happens of population when t greater than t naught. Okay, so that is our problem. Okay. So by this thing, it is very easy thing. So yeah, that is rate of change, just it's varying in a proportional to the population size. So we will get a linear model. Linear model means the operator acting on the solution y is linear. Okay, and this linear means it is the linear algebra, the linear transformation, that properties will come into the picture here as well. So this is the linear model we are getting, and this is initial value problem. This is such a simple model which easily can predict if this is the situation. Under this situation, how the future dynamics will look like of the population. So this can be easily solvable. This and its solution is nothing but in terms of y naught into e power r into t minus t naught. Okay, but now one thing you observe, that suppose r is greater than 0, that is usually the case for a population to increase, because birth rate should be bigger than the death rate and so on. Okay, so what happens then? Yt is converging to infinity as t tends to infinity. So if you observe that in this solution, if time grows, the population is moving towards infinity, but that is not the case usually, right, in real life. So what happens when population grows, then certain other criteria comes into the picture. Other species may try to encounter them. Even in between the species, there will be fight and the growth will be reduced. So this linear model is not very applicable usually. Okay, so when it is applicable, when population is very small and you want to predict in a small time. Okay, so no population can grow indefinitely, and if population becomes large, then the competition among the population entities will also come into the picture. So this type of linear model only applicable when population is small and small. So what happens? Suppose we assume that, or from statistical data, we observe that this number of encounters of two members is basically proportional to y square. Then what happens? Our model will basically reduce to this dy dt equal to ay minus by square. And this initial data will be same, and a and b is positive constant. So the growth rate is reducing. So this model is now, this model, if you observe, this is not a linear model, it is a non-linear model. And you will see that this model is much more applicable than the earlier one. Okay. Of course, B is small compared to A, because you can see that your growth it's a linear growth, and some extent it is going for proportional to y square, that is only reducing the growth. So that is B is small compared to A. So here also you can get your solution of ODE. Okay. What you will get, this is the solution structure of ODE you will get, but that will not give you much idea how the solution and other things are behaving. So that's what the mathematical qualitative analysis comes into the picture. So now if you observe that, if you start with 0, if y of t naught is 0, with this model, what it will give, your actual solution will be identically 0. Okay, so this is one thing. Another thing, if you start with a by b proportional to a by b, then the solution will still be a by b even after time t naught. Okay, so this is basically the critical points. Okay, you can see from a differential equations the model, that these are the critical points, that if you start with 0, the solution remains at 0. If you start with AB, solution remains at AB. So what happens if we start in between 0 to AB? So that is the question now. So that will also answer that to answer this question, that what happens the solution y of t when it between 0 to AB. So that requires certain existence uniqueness theorem, that eventually the solution will also belongs to this 0 to, that you can observe it if I represent the solution in a little different way, y of t equal to in this fashion. Then if we go for the logistic curve, you will see that this is basically the curve is going on. Okay, and you observe that several things can be observed, that up to a by 2b, the population is growing, and also it is growing with a accelerated growth. And after a by 2b, population is still growing, but it is not with the accelerated growth, it is decelerated. You can see that. So this type of curve is called as logistic curve. So what are the things we have observed in this? That a by b is the limiting population, and dy dt is always increasing. If you can see from that, that dy dt is 0, so y is always increasing. And if we compute my du to y dt2, then we understand why up to a by 2b our population has accelerated growth. Okay, because when 0 to y naught by a by 2b, then we can see that d2y by dt2 is also greater than 0, and it is growing. Okay, so dy dt is increasing, and it is the other way when it goes above a by 2. Okay. And one more case, of course, we have to see. So initial data can also be, we can start even bigger than a by b. If we start bigger than a by b, what happens? Our dy dt will be less than 0, as well as d2y dt2 will be less than 0. So again, population will be decreases with a decelerated growth, and it will go to the limiting population. And what is limiting population? It is again a by b. So as we observe that when we have certain model, even after getting the solution, we try to understand how the solution behaves, how and what are the things is associated with the solution, with the time, how the solution converges, what is the limiting things, all things we can understand from a certain case study. So this is just a preliminary things in differential equations. So such kind of models in a much more complicated way, or much more to the real situations, you can always adapt such kind of model. And remember that to address certain problem, one model is not enough. So when the situation changes, you have to address such kind of situation into your model, and then you have to study those models. Okay, so that is the bottom line of any such ODE models and so on, or for instance any other model as well. So this is one such very simple case study. If you are interested, you can always go through such kind of many models are there in ODEs through, and basically this whole subject got developed from such kind of model. Okay, so this is some of the references which, if you are interested, can be further, you can go through these references, and it has lot of varieties in that. You can slowly get into the topics of ODEs. Okay. And with these references, I just end with one statement from Thurston, that mathematics is basically not about numbers, equations, computations, or algorithms. You may think that initially we always think that it is maybe only numbers or equations or some computations. It is not actually. It is all about understanding. Even here also you see that how you understand the solution, that is very important. How you understand the problem, it is not you get a solution, that is not enough. Okay, and here of course the whatever example or case study we have chosen, it is not usually that difficult, but it can happen that you have such model, you will not get an explicit solution, but still you can able to understand how, if solution exists, how it will behave, how it will look like, how it will go with time, how it will evolve with the time, and those. Okay, so I am ending the lecture here. So I thank you all for attending this lecture, or for your kind cooperation and present for this lecture. If you have any questions, you can ask me.
Thank you, sir,
Yeah,
for
thank
your
you.
nice presentation. I think many students present here and they are surely benefited from this lecture. You
Yeah, thank you.
started
Thank you.
from rooted level and explained
Yeah.
all in very easy way. So I think it was very easy to understand. You explained origin and historical remarks, fundamental issues in case study, all were very nice. And many participants informed us their comments very informative, excellent, etc. So I thank you. I thank you so much, sir.
Okay, okay. Thank you, Mushiba, for your kind words. Yeah.
Now interaction session, as
Okay.
we don't have too much time in our hand,
Yeah, yeah.
so
I hope I have not taken much time.
I request Mr. Niyar Sarkar, member of advisory committee and assistant professor of mathematics of this college, to start the
Yeah.
session. Mr. Sarkar, please start.
Thank you, Ramanda. Dr. Tanmay Sarkar, sir, thank you very much for your wonderful lecture. It is so informative. We are received lots of comments in our YouTube streaming chat box. So, sir, I am directly going to the questions. There are lots of questions. The first question is from Kushanta Dhawar, Assistant Professor, Balruhat College. Is it single species population group model?
What is that? Single?
Single species population growth model.
Yeah, yeah. It is single space. Single species. Yeah. We have not taken any other species into account. Then the model goes much more complicated and other things has to be incorporated. It is just a single species study.
His next question is, what is the point of inflection in the logistics growth curve?
Okay, point of inflection you can easily find out. You can see that you already have seen the derivatives, and you can find the second order derivative and you find out the point of inflection. That where it is basically getting from convex to concave and so on.
Thank you, sir. The next question from Nitesh Soni. What about recent research scope on ODE?
What about recent
Recent
research?
research
Research,
scope. Research scope.
research
Research
scope. Okay,
scope
okay, yeah, yeah.
on ODE
Research
mainly.
scope in ODs. Yeah, yeah. So basically, you can see that ODE has lot of scope because once you get into a different kind of models, the you or different kind of situation you counter, your models will get much more complicated and so on. So, and once the model changes, your whole analysis will be changing. Okay. So there is lot of scope in that, and not only in ODs, there is much more scope in PDs and in the partial differential equation, because in the current scenario of real life things that several variables comes into the picture, you might not be working with a single variable, so it requires you need to address this variable will be with other variables, how it is changing, and then immediately when you have more than one variable, the PDE comes into the picture, and once PDE comes into the picture, then things will be much more complicated, and this whole knowledge of OD will comes into the picture when you go for a PDE things. Okay, in a start, because PDE does not have usually does not have a solution what we can approach only through ODs. Okay, so that is one of the main approach to the solution of ODs. So this all the problems, all the concepts of ODs will comes into the PDE thing. So if you really want to understand the ODE things better, so there are two things you can say. One is that when models get get much more complicated when you encounter several things, like as one person asked, that when you encountered with multiple species and so on, so the problems keeps on get complicated, and that will require a total completely different analysis for that. Okay, so that is one of the scope. Another scope, as I said, in a PDE things, you all require these ODE things to study that. Okay, I hope that will make you understand little bit in the research thing. And of course, as you see in the ODE things, that once it get complicated, different types of analysis will be required: real analysis, multivariate analysis, all what you have studied, all things will come into that topics. Okay, yeah, Nihar Babu, you can continue. Yeah.
Thank you, sir. Next question. What is the significance of differential equation having no solution?
Yeah, so what happens, how this differential equation comes into the picture? Okay, so it comes into the picture from a problem, okay, or from a real life problem, that this differential equation comes into the picture. So it can happen that you are not able to get a solution in a proper way, or in a differentiable form. You may not have a certain solution. Okay, so then what happens, what you have to do, you have to go much more in an advanced way, that where the solution exists. So it may not see what usual idea for us, that if something is a solution for a differential equation, means it has to be differentiable. So it may not be the case always. Okay, later when you go much more deep into the topics, you will see that not always differentiable functions will be a solution. It can be continuous, it may be even discontinuous. Those kind of function can also be a solution of a differential equation. So such kind of things can you can go through later on. If you go much more advanced, you will see that this type of situation arises, that because many times you have to give a solution to the problems, right? Because this is coming from a real life things. So how to give such kind of things? And the world is usually that not with the nice functions. Okay, you mostly, actually now you rarely get any differentiable function as a solution. You mostly have to deal with such discontinuous function solution and so on, and there only this analysis, everything comes into in a lot more impactful way. Okay, yeah.
Thank you, sir. Next question from Rizal Mehdi, our student.
Yeah.
How differential equation explains gravitational force? How differential equation explains gravitational force?
Yeah, it not basically in that way. It is not expressing, it is expressing. So what I have given you, it is just basically a force. Okay, and if you want to understand, it is a gravitational force. Suppose, as I give a one instance, that suppose a ball is falling from top. Okay, so the gravitational force will be impacted on that particle which is coming from top to bottom. Okay, so then when you study its equation of motion, there this ODE will comes into the picture. So, and that equation will involve that gravitational force. There you can further go ahead to address how the solution of things will be applied. So basically, get the expression of ODE, or to make construct the ODE with the gravitations, then only the ODE will comes into the picture. There itself that gravitational force will be involved. So basically, to model that problems, this gravitation comes into the picture. So yeah, Nihar Babu. Yeah, Nihar Babu, we can go to the next question.
Due to lack of time, our last question is from Obiro Bhattacharya. The most common question: what is the importance of differential equation in our daily life?
Okay, so you can see that, right, that several models, we just discussed one case study, so there are several such kind of example, like as we said, one of the main differential equation things comes with certain another topic with the control theory and so on, and that has been basically mainly used with in ISRO, ISRO, and so they basically use for artificial satellite, how the projector will go, at what speed it has to go. So there are certain extent of this type of problems, and there is also this you can see this population is irrespective of any population, any species. So this type of models comes into in a different way, like in a mechanical vibration that you use in many mechanical engineering, that how this vibration will goes and so on. So basically, where this rate of change things will come, the differential equation also comes into the picture. So it is such a common criteria or common thing that many times we just encounter this type of differential equation. So it has lot of application in daily life. Once we go for different models, this things comes into the picture. Okay. Yeah. So I hope that to make you understand a little more. Yeah, Nihal Babu, we can.
Thank you very much, sir, for your patience for answering the questions. Here the question answer session is over.
Okay.
Okay,
So,
thank you, sir. Also, thank Mr. Sarkar for conducting the interaction session in very nice and efficient way. And now I request Dr. Rita Chandra, Joint Convener of this webinar, Associate Professor and HOD, Department of Mathematics, City College, for vote of thanks. Your microphone is mute. Ma'am, your microphone is mute. Please unmute it. Okay, thank you.
Good afternoon, everyone. It is my privilege to have been asked to propose a vote of thanks on this special occasion. I express my sincere gratitude to our respected principal, Professor Sheetal Prasad Chattopadhyay, for providing encouragement and support to us. I am grateful to Professor Tapun Ghosh, coordinator of IQAC, for his enormous cooperation. I would like to extend a very special vote of thanks to Professor Tanmay Sarkar for giving us his time and sharing with us his valuable knowledge and opinion today. He has made a very interesting presentation on ordinary differential equation, which is informative and which I am sure has highly enriched us all. Our heartfelt thanks to Dr. Sarkar again. Now I am express my sincere thanks to all the members of the advisory committee, Professor Supriti Sarkar, convener of Research, Development and Seminars Organization Subcommittee, Professor Uttam Bera, and Professor Neha Sarkar of Mathematics Department, City College, for their valuable and active support. I am very thankful to the organizing secretaries, Professor Masiur Rahman Sardar and Professor Shamsundar Dhara, Mathematics Department of City College, for taking initiative and putting effort to make this webinar a success. I also thank and appreciate the joint conveners of Technical Committee, Professor Shandip Prasad, Hindi Department, and Professor Atanu Sarkar, English Department, for their full support and technically conducting this webinar. Finally, I, on behalf of Mathematics Department, City College, am very happy to express a hearty vote of thanks to all the participants, without whom this webinar would not have been a success. Thank you, Professor Sharkar. Thank you all. Have a lovely day.
Thank you, madam. So we end our program here now. Please leave the platform, everybody. Thank you.
Yeah, thank you, sir. Thank you, Mushir Babu. Thank you, Rita Madam, for this nice words. Yeah. So
thank you, Dr. Sharkar.
Yeah. So this time we could not meet all of you physically, but hope we will meet sometime physically sometime.
Sure, sir.
Yeah. Thank you for your nice organization and nice effort. Okay. Thank you so much.
Thank you.
So shall I leave? Shall I leave?
Yes.
Okay. Thank you.